In this video, we'll apply what we've learned about describing vectors in terms of components, finding their magnitude, and discussing scalar multiplication and how that can be used in a physical context, such as this example here. So I have an object that's moving along a straight line, and it's moving with a constant speed, so moving along a straight line in space with a constant trajectory, or a constant pace along a straight trajectory. Initially, it's observed at the point P, whose coordinates are 1, 2, 3, and then 5 seconds later, it's observed to be at the point Q, whose coordinates are 4, 4, and 4. We're going to look at different ways that we can use vectors to describe what's happening physically. The first thing you might look at is the displacement of the object over this 5-second period. It moves from P to Q, and so we might look at that vector PQ. That would be the displacement of the object. In order to compute the displacement, you're just going to calculate the change in coordinates of the points that you've observed it at. So it'll be 4 minus 1, 4 minus 2, and 4 minus 3. And those will be the components of a vector. So now I've changed to angle brackets to indicate a vector, as opposed to parentheses, which indicate the coordinates of a point in space, a location. In this case, we'll get 3, 2, 1. Each of those quantities, if they're lengths and perhaps measured in meters, would have units of meters. So we'll say that this vector PQ, which is a displacement, has units of meters. You could then find the length of that vector, the magnitude of that vector. In this case, that would indicate how far it traveled over that 5-second period, so the actual distance traveled. In order to compute that, you sum up the squares of the components. Since they're in meters, right now you have squared meters, so it's not length. And you take the square root of that now to come back to length, and you get square root of 14. And again, that is a length, so it's in meters. This object travels square root of 14 meters over this 5-second period. Another natural thing you might look at is the velocity of the object. Velocity is a vector. It's the change in position, that's this displacement, over the corresponding change in time. So for us, it's the vector PQ, which is in meters, and we'll divide by the fact that it took 5 seconds to get to those 2 points, between those 2 points, so I'll divide by 5 seconds. What I'm doing here is scaling the vector. I'm taking that vector PQ, and I'm scaling it by a factor of 1/5. So each of the components will be scaled by a factor of a fifth, 3 over 5, 2 over 5, 1 over 5, and I get a new vector which we'll call v. That's the velocity. It is a vector which indicates the direction that it's traveling, and its magnitude indicates how fast it's traveling. In this case, it would have units of meters per second. Again, the magnitude indicates how fast it's traveling. That we would call that speed in physics. So speed is the magnitude of the velocity vector. Sum up the squares of each of those components, 9/25, 4/25, and 1/25. Take the square root of that to get back to the length of that vector. And since each of those quantities, each of the components was in meters per second, this result will have units of meters per second. It will be square root of 14 over 5 meters per second. Not a shocker here. You should see our principle from earlier. If I scale a vector by 1/5, I should end up scaling its length by 1/5. And indeed, I see square root of 14 being scaled by 1/5, multiplied by 1/5 now. If you want to know the direction that the object is traveling in, well, the velocity vector or this vector PQ, its direction indicates this, but you would like maybe a more standardized definition of what direction might be, and one way to do that might be to normalize the velocity vector. So you might take v and normalize it to get a unit vector that points in the same direction. Here I'll take v and divide it by its length. That's called normalizing it. Now PQ also points in the same direction as well, so you're welcome to take PQ and normalize it, which means divide by its length. Both of these will be unit vectors pointing in the same direction. They'll be the same vector, which we'll call u. I need to take PQ, 3, 2, and 1, and I need to divide each component by the length of PQ, so I need to scale it by 1 over the square root of 14. This is a new vector. It will have length 1, so u is a unit vector, and it points in the same direction as the direction of motion, either given by the displacement vector or the velocity vector. Notice that this vector has no units. You've taken the length, which is pq in meters, and you've divided by its length, which is in meters as well, and it therefore has no units. So when I talk about the direction of a vector that maybe had units attached to it, you end up getting a resulting vector, which is what we call dimensionless. It has no units attached to it.